So for this first problem, I gave you guys an early voltage to use. So I'm not expecting you to just assume R naught is equal, VA is equal to infinity and R naught is equal to infinity. Some of your emails, I got mildly scared in as much as people were saying, oh, well, we're just going to assume the early voltage is zero. That doesn't work because that means the slope of your curve would be infinite. Or effectively your device would be working as a diode. So that's a terrible assumption to make. If you were going to make an assumption about anything, you should assume that VA would be infinite, which means your slope would be flat and your collector current would be a constant thing. I understand what you meant, but numbers and all of that kind of stuff technically do matter, even though I'm just as bad as you guys about remembering to put them down. So anyway. So for this first problem, you have an early voltage and all of that kind of stuff. For answering part A, using the direct analysis relationship developed in class, calculate the location of all the poles and the zeros. And I think North was the one that found this. One of the equations that I gave you, I forgot to include two capacitances in it. And so the units work out really, really wonky when you're looking at the amplifier stage. So just as a quick recap thing, let me find the notes. We're not going to do any derivation whatsoever. I'm literally just giving you the equation correctly. So for a common emitter amplifier, low frequency response, the coefficient A of the second order polynomial that is in the denominator of our input stages response should be, or actually let's do it this way. I gave you RE times R sig times R pi plus R1 in parallel with R2 plus R pi times R1 in parallel with R2. What I want you to add to that is literally just multiply that whole thing by Cn times Ce. That should make the units of this ohms times seconds squared, which is what it should be for that particular polynomial. Okay. Another thing that I noticed in my notes, and I'm not 100% sure of quote unquote how I taught it to you, so I just want to be clear. For I think it's part B, where I'm asking you to calculate omega low, that should be the sum from I is equal to 1 to n of 1 over the various time constants. So because there are 3 capacitors, it'll be 1 over tau 1 plus 1 over tau 2 plus 1 over tau 3. I think I originally gave it to you as just the sum of the time constants, not the sum of the reciprocals. The sum of the time constants is obviously just going to be some amount of time, not a frequency. So you use the reciprocals for frequency. Yes?
Is that give a third?
Radians per second. So just to be clear, this will be measured in radians per second.
Are all of the formulas for omega?
They are all in radians per second because they're all omegas. If you want any linear frequencies for poles, zeros, etc., just simply take your omega and divide it by a factor of 2 pi. So for instance, in problem 3, when you are calculating your bandwidth, I would calculate that as omega high minus omega low divided by 2 pi, because the bandwidth is typically expressed in hertz. Speaking of problem 3, Hannah, thank you for bringing this to my attention. I didn't give you guys a drain current to use, which means you couldn't even really get started on this one. So now you're given an actual drain current. Everything else should be fairly straightforward. Yes.
When the short circuit, open circuit, at what point do we say the bottom section is not?
So if it's within 10%, I would say it's fairly valid. And if it's outside of 10%, it kind of isn't. It's really a judgment call kind of thing. Effectively, I believe, it should be a bad approximation, at least for problem 1 and 2, because we don't have a dominant pole effectively. So the highest frequency thing isn't far away from the lower frequency ones. There's 2 that's, I think one is like 1.7 kiloradians per second, and another one is like 3.6 kiloradians per second or whatever. So because it's within the same decade, there's definitely not a dominant pole kind of thing. So that's why it works out not great.
The amplitudes of the poles. So on number 1, a lot of my poles I got were negative.
They should be, yeah.
Okay, but my omega low is positive.
Right, yes. So all of those, so this goes back to stability that we talked about in 224, right? So if we're looking at a pole 0 constellation, I think we talked about that very briefly. Effectively, we want our poles to be in the left-hand plane because that tells us that we have a stable system. If we had poles on the vertical axis, that means we have a marginally stable system or conditionally stable system, and then poles on the right-hand side tell us that we have an astable system. So if we want all of those poles to be negative, we're realistically only looking at their magnitudes, because what does a negative frequency actually mean? Nothing. Yeah. So it's impossible to get a negative number using the short circuit time constant method or the open circuit time constant method, because everything you're putting in it is positive. So comparing magnitudes is exactly what you could be doing. Brody.
On number 2, where it has to solve with the binder I,
Mm-hmm.
in the notes we have I and DD plus D2.
Look later on to where I talk about the transit frequency, FT, because that's the only transit frequency, and transconductance, GM, should be enough to get you to calculate C pi. So I may be misremembering, but our transit frequency, FT, was GM over 2 pi C mu plus C pi, which can be approximated as GM over 2 pi C pi. This is the relationship that I use to calculate C pi. So it's just GM over 2 pi FT. If you wanted to get fancy and extract it out of this one, that definitely wouldn't be wrong. I was just lazy and in a hurry. Didn't want to do the algebra in my head. That should be in your notes.
For that, I couldn't find. You talk about the forward-based transit time.
Mm-hmm.
So I assumed the transit frequency would be converted to that, but that relationship I couldn't find.
Well, son of a gun. Oh.
It's high frequency transistor model on April 15th.
Yeah.
Okay, I may have just missed it.
Yep.
It's towards the end of.
Yeah, it would have been literally one of the last things that we talked about. Yeah. Because that's literally how you would get that from the data provided in a data sheet and all of that kind of stuff. They're going to give you the transit frequency, and then the value of it depends on the operating point of the device, which is represented by the transconductance GM. So yeah, 100% correct that I didn't give you the base emitter, or excuse me, the junction capacitances, because I you really wouldn't have access to those values even on the data sheet. All right, so I hope at this point, I have clarified all of the issues regarding homework set number 6 because I solved them all. Got numbers that at least made sense to me. So worst case scenario, the equations are giving us numbers, which, yes.
Make sure I understand.
Sure.
So for omega low and high, you have a dominant pole. Is that supposed to be roughly equal to that dominant pole or?
Yes, so it should be roughly equal is the key there. It's never going to be exact by any stretch of the imagination. So always get these backwards. The short circuit time constant approximation, which is used for low frequency, should give you a value that I think should be a little bit less. So it should underestimate, I guess, where the mid-band begins, and the open circuit time constant approximation, whichever one is used for high frequency, should effectively overestimate where the high frequency begins. And for what it's worth, I believe the Miller method, let me draw this out here, right? So if we had omega z, no, excuse me, omega p 1 here and omega p2 here in the high frequency response. If I'm remembering correctly, the Miller method is going to push these in a little bit. They're either both going to be in or they're both going to be out. I don't remember exactly off the top of my head, but they're both going to be moved in. Yes. No. So that's intentional. And the reason I just can't think of a way to really format it well that makes any sense. And also it's literally just using the equations from the notes. So if you put the equations in MathCAD or whatever correctly, and you use the circuit parameters that I'm giving you, it will spit out the answer that we're looking for. So I don't know how it could be any easier than that. When you're looking at the third problem with the MOSFET, you could take the time to actually look at the resistance that each capacitor sees, or you could literally use the exact same relationships. So for instance, the capacitance C pi is analogous to the MOSFET capacitance CGS. So it's going to see roughly the same resistance, except that everywhere that you see R pi, treat it like an open circuit. The capacitance C mu, its MOSFET analog would be the capacitance CGD. So again, it's the exact same resistance, but everywhere you see R pi, treat it like an open circuit. CCS, for what it's worth, has an analog of CDB. CSB does not have an analog. So if you have any circuit where the source body capacitance isn't short-circuited on both sides or connected to ground on both sides, you will have to actually find the resistance seen looking in through the terminals of that capacitor, which should not be a thing for the high frequency response of a common source amplifier, because the emitter to generation capacitance CE is treated like a short circuit in our high frequency response, which means the source is always at ground in the high frequency response. In the common gate amplifier, which I just put the homework assignment for that up earlier today, that CSB will, I haven't done the small signal look at it, but I think that CSB will not be 0 because the source isn't at ground. There's that source resistance RS. Let me draw it out here. So just for shits and gigs, we would have VDD R1 R2. I'm going to call this capacitance CG. And if I'm being entirely honest, I'm not even sure that that capacitance is necessary in the MOSFET, but I included it there just in case. Yeah. RL. Here's B out. CN. RSig. VM, right? So this is what it would look like for low frequency. At high frequencies, we would turn all of these capacitors into short circuits. Like so, and then we would have, let's see, so here's my capacitance CGD. Here's my capacitance CGS. Here's my capacitance CSB. Here's my capacitance CVB, where we're making the general assumption that our body or our substrate is always tied to ground for an NMOS station. And it would be tied to the positive supply voltage for a PMOS station. So in this case, CSB isn't shorted on both sides. So you will actually need to look for the resistance, which to me looks like it's going to be RF in parallel with RSig in parallel with whatever we see looking up into the solar terminal. Which I think would be one over GM in parallel or not, but I'm not 100% sure on it. Something akin to that. Nothing wildly gross. Hannah. So, great question. So for problem number 2, where I say CCS is selected, treat it as a 0 farad capacitance in your math sheet. Literally the exact equation we're going to say CCS is equal to 0 farad, put the unit of farad on there so it doesn't tell you there's a problem with the unit. And then you literally don't have to make any modifications whatsoever. Be as lazy as you can be. Lord knows I am. Any other questions regarding homework set number 6?
Everything. Second section.
Yep. So like I said, homework, I put homework 7 up today. I'm going to try to get homework 8 up. I'm going to try for today. We will see whether or not that happens, but it will definitely be up at some point tomorrow at the absolute latest, and the test as well. The design project will be due literally at the end of the quarter, and I'm going to try to get that knocked out this weekend. I just need to format some things. And I'm even considering making the design project significantly easier and not making you guys learn how to do electric and just do everything in LT Spice, just so that it doesn't take you a bunch of time. Yeah.
Are we only having one design?
Yep, just gonna do the one thing. Yeah. I'm sorry, got busy, forgot, et cetera, et cetera. Not a particularly good excuse, but it's the truth. So one design project, yeah. And if it wasn't ABET and tax related, I wouldn't even bother with it, but I need the data, so. Anything else? All righty. So, when we finished our lecture last Friday, I believe we had just talked about using negative feedback as a tool to reduce noise in our system. So we're going to talk about two other properties of negative feedback today really quickly, and then we'll do stuff that's more specific to amplifiers, and then finally circle back around to transistor circuits, which is what we're all doing. So the first property that I want to talk about today is the bandwidth extension. And I'm probably going to talk about this more. It's definitely applicable to transistor circuits. And that's what we're going to be talking about a lot next week and all of that kind of stuff. But for today, I'm more likely going to be putting things in context of an op-amp because we're familiar with that. And I believe you guys have done experiments in 229 about calculating the unity gain bandwidth product and all of that kind of stuff. So let's say that we have a simple amplifier where I'm going to just call this A1 as a function of S. We have some mid-band gain AM, and then we have a single pole in its high frequency response, so that its transfer function would look something like this. If we were to apply negative feedback where K is independent of frequency. So let me ask you guys a question before we hit you, or I hit you with this next mathematical expression. What kind of network do you think K must be composed of to be independent of frequency? Resistors. Yeah, exactly. A resistor network, okay? So if we were to apply a negative feedback network where our feedback factor K is independent of frequency, our gain with feedback, or our closed loop gain, AF, as a function of S, would be AM over 1 plus S over omega high divided by 1 plus K times AM over 1 plus S divided by omega high. So that's just the A over 1 plus KA form that we would expect from a negative feedback system. If I were to multiply this, get rid of this, by 1 plus S over omega high divided by 1 plus S over omega high, I would be clearing out those denominators, and what I'd be left with is AM divided by 1 plus S over omega high plus K times AM. Are we all okay with that? Anything seem weird? Okay. So now I'm going to do something that's going to seem a little odd. I'm going to multiply by 1 over 1 plus KAM over 1 over 1 plus KAM. And what that gives me is AM divided by 1 plus KAM over 1 plus S divided by 1 plus KAM times omega high. So from this, we can see two things. Our closed loop gain is nothing more than AM over 1 plus K AM. So that means the magnitude of our open loop gain, not worried about the frequency response portion of it at all, but just the magnitude, has been divided by the amount of feedback that we put on it, right? 1 plus KAM. What's happened to our bandwidth? Well, now we have 1 plus KAM times omega high. So our open loop gain got reduced by one amount, and our bandwidth got extended by literally that exact same amount. Now, whether you guys realize it or not, you've literally done this before numerous times, right? So if we were to look at the frequency response of an op amp, so let's call this F, and let's call this the magnitude of A1 as a function of omega. This plot usually looks something like this. So it's flat at very low frequencies, and then it rolls off. And if it's a single pole op amp, it rolls off at a rate of negative 20 decibels per decade. At this point right here is 0 dB. Then this frequency right here is the gained bandwidth product. So if the gain is 1, that represents the bandwidth. Well, when we apply a resistor network to change the open loop gain, or to reduce the open loop gain down to some closed loop gain, we're really just looking at this part of the curve. And the smaller that we make our closed loop gain, the more bandwidth we have. This is literally what we've done every time we've employed a negative feedback op-amp circuit. We've lowered the open loop gain from the ballpark of 200,000 or so for a 741 op-amp down to something more reasonable that's just established by the ratio of the resistances that we apply. If it's a inverting amplifier, it's negative R2 over R1. If it's a non-inverting amplifier, it's 1 plus R2 over R1, and we extend our bandwidth in doing so. So now we have a more formal explanation of why bandwidth extension works. All right, the last thing that I want to talk about is very much related to this, and it's going to, I don't know, possibly bring back some nightmares or something from circuits too. Let's talk about linearity improvement really quickly. So, do any of you guys remember from circuits two? This would have been probably the second or third lecture where we were talking about open loop op-amp circuits. We talked about the linear range of an open loop op-amp circuit. Anybody remember that even vaguely? Most of you, it's been a hot minute since you guys took that class. That's perfectly reasonable. Okay. So what we learned in circuits 2 was effectively that our linear range was nothing more than VCC minus our negative supply voltage divided by our open loop gain is less than our input signal is less than VCC plus over our open loop gain, right? So for just as a circuits 2 related example, for a 741 op amp, AVOL is typically on the order of 200,000 volts per volt. Let's say that VCC plus is 10 volts and VCC minus is negative 10 volts. What would our linear range be? So 10 divided by 200,000. See if I have a calculator here. I should probably be able to do that in my head, but I don't trust anything right now. So this would come out to effectively be negative 50 microvolts is less than our input voltage is less than positive 50 microvolts. Meaning that any signal that we were trying to amplify outside of that incredibly small range would cause us to hit saturation distortion, cause our output to saturate to our supply voltage of VCC plus if the signal was greater than 50 microvolts, or saturate to VCC minus if the signal was more negative than negative 50 microvolts. Well, our linear range equation isn't going to change really at all for a closed loop system where negative feedback is employed, except that instead of having our open loop gain there, we would just replace that with our closed loop gain, right? So if instead we had a closed loop gain, AVCL of, let's just say 10. Right? Now our linear range would go from negative 1 volt is less than VN is less than positive 1 volt. Right? So our linear range is much, much wider because we employed negative feedback to bring that open loop gain down to a level. So effectively, employing negative feedback makes us significantly less likely to put our device in a saturation position where our output does not change from a subsequent change in input. We obviously still have to pay attention, which is why supply voltages and all that kind of good stuff are so important, depending on what the gain you're trying to achieve with an op amp circuit is. But again, relating stuff back to stuff we've seen in previous classes, this is a pretty darn good explanation of why negative feedback improves the overall linear system. All right, so we have talked about numerous different properties of negative feedback. Let's now talk about types of amplifiers. Okay, and this is how we are going to classify things. Okay, so we're first going to talk about the sense mechanism of an amplifier. Okay. So we only have two options. So first, if the output signal of interest is a voltage the feedback network must be connected in parallel. I'm going to put a word here you may have heard before. We commonly call this placing the feedback network in shunt with the output. Of the open loop amplifier circuit, okay? So if we were looking at just the output side of a closed loop amplifier system, might look something like this, okay? So we're on the right-hand side of an open loop amplifier. Typically, the right-hand side in our signal flow diagrams is representative of the output of a particular stage. So we might have some terminals here like so. Representing the output voltage of this stage. So let's call that V out. And then we would need to connect our feedback network in parallel. So we would tap off the positive polarity terminal and connect it to the positive polarity terminal of our feedback network. And we would tap off of the negative polarity terminal of our open loop op amps output and connect to the negative polarity terminal of our feedback network. I'm going to call this port 2 of our feedback network, and we'll talk about what that means more in a little bit. So one interesting thing that we would see here is that if we were to look in to the output terminal and determine our output resistance with feedback, so that's what that ROF means, output resistance with feedback, we would find that that is nothing more than the output resistance of our open loop circuit, R naught, divided by a factor of 1 plus K A1, where A1 is the gain of our open loop amplifier. So effectively, placing this feedback network in parallel lowers the output resistance by a factor of 1 plus AA. Contextually, as an electrical engineer, does that make sense? If I put a resistive network in parallel with an output resistance, it's going to get smaller. Absolutely. So nothing particularly wild or crazy there whatsoever. Now, instead, if our output signal is a current, the feedback network must be connected in series. With the output of the open loop amplifier circuit. So redrawing our little picture from above, that might look something like this. So here's our open loop amplifier. Here are my output terminals. Down here, I'm going to have my feedback network. Port 2. So I'm going to define my output current as flowing in to the output port of my open loop op amp. What we would do is we would short circuit those output terminals, and then we're going to break this negative path like so to connect our feedback network in series so that our output current on its effectively return path winds up flowing into the positive polarity terminal of our feedback network. If we were to look at the output resistance with feedback here, because we're connecting our feedback network in series, we should see that our output resistance gets boosted, and it will be boosted by a factor of 1 plus Ka. So we can manipulate our output impedances, either make them higher or lower, by connecting our feedback network in either series or shunt, but that limits us to the type of signal that we can measure using this network, right? So a shunt connection allows us to measure a voltage at the output. A series connection allows us to measure a current at the output. So now what we're going to do is we're going to look at the mixing or the return path of things. I'm going to start this on a second page so that there's enough room. And do I need to scroll back up for you guys? Right here, okay. Yep. So this is effectively what our is playing the role of our summer in the signal flow diagram, right? And so once again, we're going to have one condition if the signal to be amplified is a voltage, and another thing if the signal to be amplified is a current. Okay. So yes. Returning, yes. Sorry for my bitty penmanship. All right, so if the signal to be amplified is a voltage, the signal source is represented by its Thevenin equivalent circuit, and the feedback signal VF is connected in series with the input signal source Vs. So that would look something like this. So this is the input side of our open loop amplifier. And then move those over just a smidge. All right. So normally speaking, we would apply our source voltage here. Realistically, I would also have some practical resistance RS in series, but that's not really bringing anything else to the table right now. So I'm just pretending like it's zero and like we had an ideal source. Our feedback network would be down here below. Here's our terminals of our feedback network, and this is going to be port 1. So if we want to put this in series, what we're going to wind up doing is breaking this path right here and connecting this guy up here like so. So if this voltage right here is our feedback voltage VF, here's my positive polarity terminal. Here's my negative polarity terminal, like so. That voltage VF is in series with our signal voltage VS. And then the voltage that is present across the input terminals of my amplifier is this error signal VI. Over here over to the side, I want you guys to tell me what VI is going to be. So VS plus VF would be positive feedback. So we can see very easily, or at least I hope we can see very easily, if we follow the current around this loop, or we're just looking at the polarities of the voltages applying Kirchhoff voltage law, VS and VF are of opposite polarities, which we very much need to be true in order to employ negative feedback. If we had positive feedback, it would constantly cause the input signal applied to the amplifier to get larger and larger and larger, eventually driving our output to saturation, which is what we are literally trying to avoid with negative feedback, right? So that error signal is nothing more than VS minus VF. A small portion of the output is subtracted from the input signal in order to keep our output stable. If we were to look in and find our input resistance with feedback, what do you guys think we're gonna see based on our prior experience? We connected it in series. So should we boost the input resistance or should we attenuate the input resistance? Boost it. What do you think it's gonna be boosted by? 1 plus Ka. Boom, absolutely right. Lastly, if the input signal to be amplified is a current, the signal source is represented by its Norton equivalent. Circuit, and the feedback signal is connected in parallel or shunt with the input signal source. So let me just draw that really quickly. So here's our open loop amplifier. Down here will be our feedback network. So let's put our current source over here on the right-hand side, excuse me, on the left-hand side. You would think at 42, I'd have that figured out by now, but apparently not. And let's see. I'm going to tap off of this positive polarity terminal of the input of my amplifier. Let me just go ahead and note that here. This is my input signal VI. So here's port 1, and this is my feedback current signal, IF, and this is my input error current, I lowercase I. And so that I lowercase I is just IS minus IF. Obviously, if we had positive feedback, it would be IS plus IF. Current would be flowing in the opposite direction, which would again cause our output to gradually move towards saturation. What do you think our input resistance with feedback is going to be? Ri over 1 plus Ka. Absolutely right. All right, so effectively, we now understand the basics. So if we want a voltage amplifier, meaning that our input signal is a voltage and our measured output signal will also be a voltage, we need to connect our feedback network in parallel on the input side and, in series on the input side and in parallel on the output side. If we want a current amplifier where our input signal is a current and our output signal is a current, we need to connect in parallel on the input, in series on the output. If we want transconductance amplifier where our input signal is a voltage and our output is a current, it's series on both sides. If we want a trans resistance amplifier where our input signal is a current, our output is a voltage, it's parallel on both sides. So what we're going to spend our next several class meetings going over is just different amplifiers illustrating each of the different permutations of this, right? So there's only 4 total possibilities represented by a voltage amplifier, transconductance amplifier, trans resistance amplifier, and current amplifier. We're going to go through those and then the class is over. So that's the last thing that we'll have time to talk about. Sorry, what? I can't even hear you. I'm old and deaf and tired and my allergies are driving me nuts. So anyway. All right, this is a good enough of the starting point, or excuse me, stopping point for today as we're gonna have. So we'll kick off voltage amplifiers on next Monday.